equation 1 from the slope of the VT graph, and equation 2 from the area under the VT graph. But now we're going to be using our linear systems of equation. So we're going to be playing the game of substitution, elimination, and so on that you learn in math. But we're going to try to keep it simple and only focus on substitution. So what I mean by that, if you look at equation 1 has V final written in terms of it. And we're going to substitute this into equation number 2, which has a V final term in there as well. So we're going to substitute equation 1 into equation 2. Well, equation 2, let's write it out. Delta D equals to V initial. But instead of V final, since we're doing substitution, we're going to write V initial plus A delta T from equation 1. The rest remains the same. Right, so just take a moment to pause and look at this. So we substituted equation 1 into 2, which is replacing the V final in 2 from the equation 1. Now is the exciting part. We're going to play some algebra games. So let's simplify this to get another beautiful equation of motion. This is our goal. V initial plus V initial, we have 2 V initial plus A delta T, all divided by 2 times delta T. So we can simplify the right side even more. And here we're going to expand it out, the delta T term inside our brackets. It's going to look a bit strange because it's reverse expansion. But on the side, this is the same thing if we were to have written instead delta T on the right side, delta T on the left side, and then our expansion that we're used to. So this is kind of like a backwards expansion, but this. So 2 V initial delta T plus A delta T times delta T, all divided by 2. So just a math aside, in case your math is not so strong, if we have, for example, generally A plus B over 2, this is the same thing as thinking as A over 2 plus B over 2. So we can split the fraction into 2 fractions. So let's see what that will look like. 2 V initial delta T divided by 2 plus A delta T divided by 2. And the left side remains the same. All right, so now let's simplify it further. Notice that the 2 will cancel out. And also notice that we have a delta T times a delta T. So that means we're multiplying the same term by itself, which will be the equivalent of delta T times delta T will be delta T all squared. This will give us V initial delta T plus 1 over 2 A delta T squared. And this is equal to the displacement. Now, technically, this is the equation. That's it. It's beautiful to some people. I don't think it's beautiful, but some people call this equation number 3. I think it looks unfinished, and Newton wouldn't be so happy with it. So let's try to get a more beautiful form of it. In order to do that, there's going to be an equation that comes out of nowhere. So recall that we define the displacement of an object as the change in position. So it will be d final minus d initial. So we're going to replace the displacement on the left side by the change in position definition. D final minus d initial equals to v initial delta t plus a half a delta t squared. Now, the last step in this, we're going to just move the d initial term to the right side of the equation, which actually really means adding both sides of the equation by d initial. D final equals to d initial plus v initial delta t plus a half a delta t square. Wow, that is a much, much more beautiful looking equation. Now, I haven't explained to you why these equations are beautiful and some interpretations of them, so I'm going to give you my interpretations of them and a way to remember them in our later video. But keep in mind that we're actually not finished. Although this I labeled equation 3 earlier, the mirror of it, 3 prime, which is the same equation just written differently, is the way I prefer. But we're not done playing this game because there's actually 5 equations and we only have 3 so far. So find out in the next video how we can get the other 2 equations.